Okay, let's take a look at a first example. A hole punch machine is set to punch a hole that is 1.8 centimeters in diameter in a strip of sheet metal in a manufacturing process. The strip of metal is then sent on to the next phase of production, where a metal rod is slipped through the hole. As such, it's important that the hole be punched to the specific diameter of 1.8 centimeters. A hole that's too small won't allow the metal rod to go in. A hole that's too big won't keep the rod in place. To test the accuracy of the hole punch machine, operators randomly sampled 12 punched holes and measured the diameters in centimeters. Say we want to be 90% confident. Okay, so this hole punch machine can't produce diameters that are too big or too small. They have to be just right. So what does that imply? That would imply equal to in the null hypothesis, not equal to in the alternative hypothesis. So here are a set of hypotheses. The mu is equal to 1.84 centimeters. Alternatively, that mu is not equal to 1.84 centimeters. Okay, again, we want it to be 1.84, can't be too big, can't be too small. If it's too big or too small, then it's not equal to 1.84, and we want to find that out. Okay, so what else do we know? We know the sample size was 12. We know that the mean of the sample of 12 was 1.8475 centimeters. And we know that the standard deviation was 0.021 centimeters. Okay? And we said we want to be 90% confident with this. So 90% confidence implies alpha of 0.1. Okay? So now let's use the critical value approach to address this. Okay, so we stated our null and alternative hypotheses. We know we're going to use a t-distribution, okay, because we have, we're testing for a population mean and we don't know sigma. We're going to use S as an estimator for sigma, okay? So we need to find the critical value, okay? So the critical value would be on the t-axis, t with degrees of freedom, n minus 1. That's 12 minus 1, or 11. 11 degrees of freedom, okay? Here's 0, and we know this is going to be a two-tailed test. How would we reject the null? If it's too big or if it's too small, okay? So too big out here, too small out here, okay? And we need to find these critical values associated with, this is 0.9 here, 1 minus alpha, 0.9 here, alpha over 2 up here, that's 0.05, alpha over 2 down here, again, 0.05, okay? So if we go look up in our lookup table, go down to row 11, degrees of freedom 11, over to 0.05, we will find that the critical value is 1.796, okay? That's the positive 1.796. Down here, this is a symmetric distribution, so we know that this value is negative 1.796, okay? So now we need to calculate the test statistic and see where it lies in the non-rejection region or out in the rejection region. So let's calculate that. T naught is y bar minus mu naught over S over root n. Okay? Here we have y bar 1.8475 minus the hypothesized value 1.84 divided by S 0.021 over root n. N is 12, root 12. Okay? And if we work that out, use our calculator, we've got 1.237. Okay? So the test statistic is 1.237. So now we compare that to our rejection regions. 1.237 lies right around here. 1.237. Okay? It's in the non-rejection region. Okay? So we're not going to reject the null. We're going to conclude that the mean diameter of the holes that are produced by this hole punch are indeed 1.84 centimeters. Okay? We have no reason to believe that the hole punch is producing centimeters that are something other than 1.84. Okay? Or holes that are something other than 1.84 centimeters. Okay? And that conclusion is being drawn with 90% confidence. Okay? It's very important that we state our conclusions with respect to confidence.